Şimdi başlattık. Okay, good morning everyone. So what's going to happen is that I have also a 2-question class exercise, but to make sure everyone is in, let's start our new topic, and maybe in the middle somewhere I will cover the exercise as well, okay? Let me share my screen again, and we will start a new topic, which is going to be mostly our last topic, basically, which is called multi-loop systems. Okay, so 407, week 13. January 05. So multi-loop systems, and you can also read this from Chow's book. Chow, it is, I believe, in chapter 10, so you can also take a look at it from over there if you want. All right, so let me say with process diagrams. Okay, so this time I will also kind of draw some process diagrams to illustrate these different architectures. Okay. Now, process diagrams are not block diagrams, but they are kind of they are diagrams which really illustrate the physical system. Okay, let me show you one version. Okay, so as an example, consider the following heating problem. So I will first illustrate our classical single loop control architecture over this diagram. Okay, so this is a problem where essentially it's a home heating problem. There is water being heated by gas. Okay, it's the classical kind of combi in our homes. Okay, so what is there? There is basically a water tank. Okay, which is being heated by gas. Okay, so we have gas fire here, and then what's happening is that cold water is coming in and just moves around this heater, and then it's just going to the heaters in the rooms. Okay. Okay, so this is the heater in rooms. Okay, so we have cold water coming in. Hot water here, and there is output disturbance. Okay, output disturbance. Which is essentially the changing ambient temperature. Okay, so depending on what the ambient temperature is, obviously there is an effect on this output. Okay, and then we have gas line, so fuel gas. But there is also a fluctuation plus minus delta Q here. Okay, so this is let's say gas disturbance. Okay, we can just put it like another disturbance over here. Okay. So what is our classical single loop architecture? And I'm going to illustrate this with a process diagram. The process diagram is nothing but just illustrating what kind of measurement and control components there are in the system. Okay. What is our control architecture? What we do usually is that we make a measurement of the output before the disturbance, because actually not before the disturbance, right? So let's put it here. We make a measurement of the output including the disturbance. Okay. Let me just draw this slightly differently. Put it here. Okay. And then what's happening is that here we make a measurement. So we have a notation like this. TT over here is notation for a temperature transmitter. It is called a transmitter because it's a measurement device that actually relays an analog output to a distant controller. It's like your Honeywell control system in the laboratory, right? Usually the measurement devices are standalone. They make the measurement, they digitize the measurement. They make the measurement, either they digitize it and send it over a network connection, or they are analog current-based, let's say, transmitters that just send a current, a constant current related with the temperature along a line to the measurement device or the digitization device. Okay, so this is like our sensor, and we also have a temperature controller. A temperature controller. Okay, so TC is temperature controller. Okay, and then this actually drives a valve. Okay, so I believe the notation is like this. Okay, so this is a valve. Okay, so it's a servo valve because what's happening is that the temperature controller drives the valve. So there is a change in the aperture in the valve. Okay, so this is our classical architecture, right? Our we can call this a single loop control architecture. So if we want to put down the block diagram of that, what's happening is that we have Tref, the temperature reference to the controller, and then we have GC, our controller, which is in this case the temperature controller, right? And then it's driving the plant. The plant is valve plus heater. Okay, everything that is driven by the controller. And then we have the output, which undergoes a disturbance, let's say D. Okay, and then we have the output, which is T out, and then that is basically measured by the temperature transducer. Okay, we can also have obviously over here an H block, which characterizes what's happening with any measurement device. Okay, so this is our classical single loop architecture. But what's the problem with this architecture, especially with this heating problem? What is specific about the heating problem is that it has a very large time constant. Okay, so what's happening is that from the fuel gas, which we control through the valve, to the temperature within the room, there is a lot of time delay. It's not pure time delay, but it's a large time constant. So when we change the fuel flow, it takes a long time for it to have an effect on the room temperature, because the fuel changes how much fire there is in the heater, and then that has an effect on the cold water coming in, and eventually it has an effect on the room temperature. Okay, so from the fuel gas to the room temperature, there is a large time constant. Okay, as long as the disturbance is at the output, that means there is ambient temperature affecting the output. Okay, so as soon as we have a change in the output, we sense that, and we can actually change the control valve in order to increase or decrease the gas flow in response to that. Okay, now we cannot do anything else, because we have to observe what's happening at the output because of the disturbance. Okay, later on we will also see we can do better than that. That means we can also try to sense the disturbance before it has an effect on the temperature itself. Okay, so that's another kind of issue. Now the one that we want to look right now at is a disturbance in the gas flow. So as you said, I said plus minus delta Q. That means there can be a fluctuation in the gas flow. Okay, and because we are changing the servo setting based on what we observe at the output temperature, this change in the fuel gas flow will have a large time to affect the output. So we will our response to that will be delayed by that time constant. Okay, so what's the alternative? What can we do? The alternative, or the idea, is that if we can also have the ability to measure the gas flow as well as regulating it with the valve, we can actually do an earlier correction to the gas flow. Okay, so if we can measure the gas flow, and we also have kind of another controller that we will call an inner controller or a slave controller. Okay, we can actually regulate the gas flow in a smaller loop so that the fuel gas flow is almost constant. Okay, so we can eliminate the disturbance in the gas flow even before it has an effect on the output of the entire plant. As we will see, mathematically this has a lot of advantages. Conceptually it also makes sense, but we will see that it has a lot of interesting effects on the system performance. Okay, so the observation is that controller in this architecture will react much later after a fuel flow disturbance is transformed into a temperature change, in the process output, which is room temperature for a large process time constant. This may be a larger problem. Okay, now we are asking what is an alternative. Okay, so the idea that we discussed is that we may also measure the fuel flow directly at the input and regulate it and regulate, let's say, through the valve to keep the flow constant. Okay? Now, this idea is called cascade control. Okay? Cascade control. We will also cover other architectures, and I'm going to draw this one in a minute. Besides cascade control, we will have disturbance feed forward, which translates to measuring the disturbance and acting on the disturbance even before it has an effect or it has a chance to affect the output, and feed forward feedback, which is a combination, and time permitting, something called the Smith predictor, which tries to deal with an ideal time delay and its effect on the plant. Okay? Now, so this idea, right? Note, this fuel flow controller cannot be the only controller in the system, because, you know, we still need to regulate the output temperature. It's not enough to simply regulate the fuel flow, because there are other disturbances in the system and there are other unknowns. Our plant model may not be exact. So even if we regulate the fuel flow to be constant, that doesn't imply automatically that the output temperature will be constant at the desired value. Okay? So this cannot be the only controller. Because the output temperature is subject to other disturbances and variations in the plant. Okay? Our inability to have an exact model of the plant and so on. Okay? So we also need the original controller, which is based on the output of the process. So let me sketch the new architecture. Okay? So what we will have is the same kind of boiler. Okay? The plant is not changed. So we still have cold water coming in, being heated out, and going to the heater. We have the fuel line. So fuel gas. We have the flow disturbance. Okay. Okay. So what we are doing is we want to do something here. Okay. So here is our valve, servo valve. So we can regulate the fuel flow, but what we want to do is we want to measure the flow. So we have a flow transmitter here. FT is a flow transmitter. You can also read this as a flow transducer as well, okay, meaning the same thing. So we want to measure this, and we want to have a flow controller, and that's going to close the loop here, okay. FC here is the flow controller. So how we're going to connect this with the output? Now the question here is that what is the reference to the flow controller? Who's going to specify what the flow should be? Now that flow controller will get its reference value. Okay, let's call this F set. Okay, the set point for the flow. That's going to come from the output controller. Okay, so we will basically have over here a temperature transmitter or transducer that's going to drive a temperature controller. Okay, let's call this TC, and that temperature controller will specify what should be the set point for the flow controller. So the temperature controller would also have a set point. Okay, by the way, I am trying to remember whether I have indicated the set point for the temperature controller here. Note, okay, we have a T set point, okay, here, the set point for the temperature controller in our classical, or this was T ref, I think, right, in the block diagram, the reference temperature. All right, so the new architecture is somewhat more complicated, okay, but it's intuitively simple. Okay, so what's happening is that you have a flow controller whose set point is defined by the temperature controller. So you have two controllers here. Okay, now the terminology, this architecture is called the cascade architecture. By the way, there can also be a temperature disturbance here, right? Or any other plant disturbance for that matter. Okay, now this part over here is called the slave loop, or the inner loop. Okay, both are popular names for this. Okay, and this loop over here is called the master loop. Okay, there are two loops within each other. It's a nested architecture. Also, this is the outer loop. Okay. Now, I'm going to draw the block diagram of this architecture, but is there any questions so far at this point? Sesiniz çok az geliyor. Biraz daha yüksek konuşur musunuz?
Master loop tam olarak neresi oluyor? Bir şeyde gösterebilir misiniz?
Master loop sonuçta şurası olmuş oluyor. Yani şu bölge, yani içerideki flow controller için set point'i tanımlayan, ya şöyle düşünebilirsiniz. Aslında loop olarak düşünürseniz master loop dediğiniz şey bütün sistem olmuş oluyor. Yani output'tan input'a kadar ve içinde bütün plant'in de olduğu loop olmuş oluyor. Yani fuel gas'ten başlıyor, output'a kadar gidiyor, output'u ölçüyoruz, oradan geri besliyoruz. Inner loop ise sadece bu flow kısmında küçük bir loop olmuş oluyor. Blok diyagramı çizince daha iyi anlaşılacak. Başka soru var mı şu anda? Let me sketch the block diagram for you, and then maybe you can repeat or revise your question. Okay. So the block diagram obviously makes the outer loop and the inner loop much clearer. Okay, so we have Tref and the outer comparison here. Okay, let's assume that so this is our T out, sometimes called the C variable, the controlled variable. Okay, doesn't matter what the variable is, but let's say the output temperature. Okay, so what's happening is that this is the result of GP, and I'm not drawing the output disturbance here, but remember that the output disturbance is over here if I sketch it after the plant model. Okay, now here's what's happening. At the outermost part, you have GCT, the temperature controller. The temperature controller specifies the set point for the flow controller, and the error in the flow drives the flow controller. Let's call it GCF. The flow controller drives the valve, GV, transfer function. Okay, and then flow undergoes a disturbance. Let's also illustrate that this also may have a transfer function here. Let's say this is the flow disturbance, L, flow disturbance. Okay, let me redraw this part. It's kind of shifted. Okay, so that this generates the flow, and the flow drives the plant. And let me also draw the temperature disturbance. Okay, let's call this D, the temperature disturbance, and then we have the T out. Okay, and over here from the flow, assuming all the measurement devices are ideal in this case, here is the flow loop. We measure the flow and we correct the flow. Okay, over here, this is the slave loop. Now it's more apparent with why it's called the inner loop, because over here we measure the output and close the outer loop or the master loop. Okay, so this is the master loop. This is the outer loop, and this is the inner loop. Okay? All right? Any questions now? So you have two nested loops, a controller inside with an inner loop, and then you have an outer loop from the very output of the entire process to the very input of it. Okay? In this case, the inner loop regulates the fuel flow, and the outer loop regulates the output temperature, which is the overall process variable. Okay? Any questions at this point? Let me give a break at this point, and let's cover our short class exercise. Hold on a second.